Now we'll be talking about the Napoleon point. So for the Napoleon point, we need a triangle ABC, and we need to form 3 external equilateral triangles. So we will take our circle tool and form 2 circles on each line segment, and wherever those points meet is going to be our 3rd point for the equilateral triangle. So now we can hide those circles and do another side. There's our 2nd point. Hide those circles and do the last side. And there is our 3rd point. So now that we have all of our points, we can now form line segments for each of the triangles. And now we have 3 equilateral triangles. So now we need to find the centroid of each of the equilateral triangles. So to do that, we will go to our midpoint tool and find the midpoint on each side of our triangles. Now that we have the midpoints, we will now take the angles for each side, or for each triangle, and form a line segment between that and the midpoint on the opposite side. So for example, we have F goes to H, B goes to O, and A goes to G, and so forth for every equilateral triangle. Now that we have all these, we can now form a point at which all 3 of the segments connect or intersect, called the centroid. So now we have centroids P, Q, and R. Now we can hide all of these objects so that it's easier for us to see what we're dealing with. So now that we've hidden all those, we now need to prove that the centroid and the vertex on the opposite side of the original triangle are concurrent. So now we can form line segments. We'll do it in a different color, from A to R, from B to Q, and from C to P. Sorry, I forgot to get rid of that segment. So now that we see that these 3 lines are all concurrent, since they meet at a single intersection point, which is S in this case. Now that we have shown that the Napoleon point in this case is point S, we will need to see what conditions is the point S outside of the triangle and when is it inside of the triangle. So obviously here is inside of the triangle, and if we take vertex C and move it around, it continues to be on the inside of that red triangle. But if we take C and put it on the opposite side, we can see that S now exits that red triangle, meaning that the Napoleon point is outside of the original triangle. For the next part, C, we will need to show if the Napoleon point can equal one of the vertices. So here, we can move C around and try and get it to equal to B, and we see that it can. Same thing for A, if we move C this way, it can, and if we were to take B and try to get it to equal to C, we show that it can. I have to use a slightly different triangle for this one just because I've had technical difficulties with the last one, but the same thing we will be showing is that the centroids form an equilateral triangle. So to prove this, we will form a line segment from each of the centroids, making a new triangle. And now we can go to our measuring tool, measure from P to Q, Q to R, and R to P. And we have that all 3 sides are equal, so therefore the centroids forming an equilateral triangle.